1996 Canadian Open Mathematics Challenge Part B. Three numbers form an arithmetic sequence, the common difference being 11. If the first number is decreased by 6, the second is decreased by 1, and the third is doubled, the resulting numbers are in a geometric sequence. Determine the numbers which form the arithmetic sequence. So they're saying that initially you've got these three numbers, let's call them x, y, and z, and they form an arithmetic sequence. So that means they are of the form m plus d, m plus 2d. That's basically what it means to be in an arithmetic sequence. Now they're told us that the common difference is 11. So they've already told you that d is 11. So that definitely helps. So that means that this is m plus 11, and this is m plus 2 times 11, which is 22. Okay, then we get to the second part, which is if the first number is decreased by 6. So that means this becomes m minus 6. The second is decreased by 1. So this becomes m plus 11 minus 1, which is m plus 10. And then the third is doubled, so that means this becomes 2m plus 44. They're saying now these three numbers are in a geometric sequence. So what is a geometric sequence? A geometric sequence is of the form a, ar, ar squared, and so on. Ar to the power 3, ar to the power 4, where r is a ratio. Okay, great. Now, one thing that helps with these types of geometric sequences is the ratio is the same. So what that means is that if you take the second number and divide it by the first number, it will be equal to the third number divided by the second number. And you can clearly see that that is just r. So that is what we have to do in this question. We have to take that component of geometric sequences and apply it to these numbers right here, these guys. Okay, so let's do that. So AR is m plus 10 over A, which is m minus 6. And that equals AR squared, which in our case is 2m plus 44, over AR, which is m plus 10. And that's it. Now we basically have an equation with one variable, and we can easily solve that. So here we go. Let's solve that. Cross multiply, and you get m plus 10 squared. And this will be m minus 6 times 2m plus 44. Okay, now we just have to expand m squared plus 20m plus 100. And this is 2m squared plus 44m minus 12m minus 6 times 44, 264. Let's put everything on one side. M squared plus, let's see here, 32, 20. So that's going to be 12m. And then minus 100 from both sides, minus 364. And I hope this factors. Otherwise, I'd have to do a quadratic. And I believe it does very nicely. 26 and 14, positive, negative. There we go. So that means m is either minus 26 or positive 14. So that means these three numbers, which were the original three? These ones, right? Yeah, these were the original three. So we got that m is equal to either minus 26 or 14. Okay, well, let's start with the first guy. If m is minus 26, then that means these three numbers are going to be minus 26, minus 15, and minus 4. If m is 14, this guy, then these three numbers are going to be 14, 25, and 36. So there you go. Those are the two possible outcomes to this question. A rectangle ABCD has diagonal of length D. The line AE is drawn perpendicular to the diagonal BD. the sides of the rectangle EFCG have lengths n and 1. Prove that d to the power of 2/3 is equal to n to the power of 2/3 plus 1. Okay, at first, there might be absolutely no clue in your mind as to how to approach this part. So let's forget about that part. Let's just concentrate on the first part of the question and see where we can go. All right, so a lot of this is already labeled, but let's do a little bit more labeling because I'm pretty confident we're going to be using Pythagoras and similar triangles because this looks very familiar to other questions. Okay, so from here to here, from B to G, I will call X. This part is already labeled as 1, so that's fine. G to C is, I believe, already given as n, right? Because EFCG has lengths n and 1. EFCG is this rectangle. And it's already labeled up here also, so that's already given. F to C is 1. We know that. Anything else that we know? Not really. I think that's about it. And I think that's all we should need. Just for the sake, DF I'll just call Y from here to here. I don't know if we'll need that, but we'll see. Okay, now we're going to label some angles. This angle in here, I will just call theta. And then this angle, of course, is also theta just because of the fact that these two lines are perpendicular. And this is just one continuous line. It's the diagonal. And therefore, this angle is 90 minus theta. The reason I know that is because this is a right angle. This is a line that's perpendicular to that line. That's how you create a rectangle. And let's see here, this angle in here is 90 minus theta. And then this angle in here would be theta. And this is 90 minus theta. And I think you get the hang of it. This is theta, and that's pretty much it. And these are all right angles in here. Okay, so let's use either similar triangles or Pythagorean theorem. From this guy right here, this little triangle, I get a Pythagorean relationship that x squared plus 1 squared is equal to BE squared. Okay, it's pretty straightforward. And then let's see here. Now I'll use similar triangles. I'm going to have this triangle and this triangle as similar. So AB from the bigger guy is the hypotenuse right here. That over BE, one of the legs, is similar to the ratio of some sides on this guy because those angles are the same. This is 90, this is theta, and this angle in here would be 90 minus theta. So the theta 90 minus theta side was AB, so we have to find the theta 90 minus theta side on the small guy, and that's basically this side, so that's BE. And then on the larger triangle, it was the 90 minus theta 90 side, that was BE. So we have to figure out that same side on the smaller triangle. The 90 minus theta 90 side is 1 on the smaller triangle. So that's basically, similar triangles, and I'm sure you've done similar triangles many times before. Cross multiplying, you get AB is equal to BE squared. Okay, well, BE squared is AB, so I can just put that in there. X squared plus 1 is equal to AB. All right, great. So a little bit of progress there, right? What other relationships can I find? Well, I can deduce that this side, AD, is the same as that side because it's a rectangle. And AD, if you look at it, at the bottom is x plus n, right? X here and here. Okay, that's pretty straightforward. Let's see, any other similar triangle relationship I can get? From similar triangles, we will get 1 over x is equal to df over n. So again, it was this triangle and that triangle that we were comparing to get our relationship. Cross multiplying, and we basically get that n over x is equal to df. Okay, I think that's all we need here to move forward with this question. Okay, so now we get into the last part of the question. Please note that this whole side right here is df plus 1. And that is the same as AB, right? Because it's a rectangle. Okay, hopefully that's not too bad. And then AB, we just figured out up here, was x squared plus 1. So that means that df plus 1 is equal to x squared plus 1. So that basically means that df is equal to x squared. Okay, great. Well, that means that n over x is equal to df, which is x squared. And then now finally, we get a relationship between the n and the x, that n is equal to x to the power of 3. And after all that hard work, we got something that's going to help us. Okay, great. Now we come to the thing we have to prove. We have to prove that. Somehow we have to prove it. But in its current form, it doesn't seem very logical. You got these 2/3, and what does that even mean? If it was squared, then you can think of a Pythagorean relationship, but 2/3 makes no sense, right? So what we can do, which is perfectly allowed, is manipulate this a little bit and see if we can get the manipulation. So we've got this d to the power of 2/3 is equal to n to the power of 2/3 plus 1. That is what we have to prove, okay? And like I said, by itself, it doesn't make much sense. So let's manipulate this a little bit. Let's raise everything to the power of 3. If you do that, you will be able to get rid of at least one of the exponents. So this part becomes d squared. That nicely sort of becomes something that looks somewhat familiar. But this one, of course, we've got to expand. And it shouldn't be too bad to expand this. You just have to write it out 3 times, and off we go. So when we expand this, we get n to the power of 4 over 3 plus 2n 2 to the power of 3 plus 1. And then we got to do it one more time. Okay, no problem. Then I got to do this expansion once more. So this is going to be n to the power of, looks like 2, because you add those guys. And that's going to be 6 over 3, which is 2, plus n to the power of 4 over 3, plus 2n 4 over 3, plus 2n 2 over 3, plus n 2 over 3, plus 1. And I think that's it, right? Yeah, okay. Let's see if we can collect like terms. N squared plus 3 n 4 over 3 plus 3 n 2 over 3 plus 1. Okay. This guy, I know you don't think it seems much better than that original one, but trust me, it will help us. Okay, so I'm going to keep this in the same screen because I don't want to get rid of it because we will need a comparison. Okay, so let's keep that in the same screen, and let's bring in our next guy, which is going back to the diagram. So if you look at this diagram, just look at this triangle. It's pretty obvious you got a Pythagorean relationship, right? AD squared plus AB squared is equal to the diagonal, which is BD squared. Right? That's a pretty obvious Pythagorean relationship. So that's what I'm going to work with in trying to get this, basically. That's my goal. If I get that, then of course that means that this is true because this whole thing is equivalent to this whole thing, right? So let's see what we can get from this whole Pythagorean relationship. From up top, it was AD squared plus AB squared is equal to BD squared. Correct? Just from that triangle. Okay, well, BD squared they had just given us was D. Well, capital D, small d, doesn't really matter. Now, what's AD squared? Do we have any kind of relationship? And we do. Up here we had that it was x plus n. Okay, so x plus n squared. What about AB? Do we have any kind of relationship? And I believe we do, if I can find it. Oh, it's right up here. AB was x squared plus 1. So x squared plus 1 all squared. And then we have these x's, and I don't want the x's, so that's where this one is going to come in. X is basically n is equal to x cubed, so that basically means that x is equal to n to the power of 1/3. Correct? Yeah. Okay. So that means wherever there's a x, I can put in n to the power of 1/3. All right. Let's keep going here then. So whichever way you want to do it, you want to do the substitution first or expansion first, doesn't really matter. I'll just do the expansion first because it's a little bit easier without exponents. So that's that, and then x squared plus 1 squared would be x to the power of 4 plus 2x squared plus 1, and I believe that this is just going to be d squared. Okay, now let's put in this substitution here. X is n to the power of 1/3. So that means this guy is going to be n to the power of 2/3. And then it's going to be 2n to the power of 1/3 times n plus n to the power of, well, n squared. And then x to the power of 4 is going to be n to the power of 4 over 3 plus 2x squared, which is n to the power of 2 over 3, and then plus 1, and that's d squared. Okay, let's see what happens now. This n squared comes out front, and then I've got, let's see here, this is combined n to the power of 4 over 3, so there's 2 of those and then 1 of those, so it's 3n to the power of 4 over 3. That's 2, that's 1, so plus 3 to the power of n2 over 3, and then we've got this lone 1 here, and that equals d squared. Well, guess what? This I've just proven, and that is identical to this guy, correct? So there you go. That means that this is true. And that's it. That's basically the proof of this question. Given positive integers a1, a2, a3, dot, 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 till an, and the quadratic function f of x is equal to the sum from I equals 1 to n of x minus ai all squared, show that f of x attains its minimum value at 1 over n multiplied by the sum of I equals 1 to n of ai, and prove that the sum of I equals 1 to n of ai squared is greater than or equal to 1 over n times the sum of I equals 1 to n of ai all squared. And then part B we'll get to a little bit later. Okay, now at first you might think that this makes absolutely no sense whatsoever, and you have no clue whatsoever of how to proceed. But don't get intimidated, I'll walk you through it. Basically, part A has to do with completing the square. Now, some of you know what this is, and those of you that don't, no problem. I'll show you with a very simple example. Let's say I gave you this equation, x squared minus 6x minus 2, and I said complete the square. How would you do that? It's very straightforward. What you do is you look at this coefficient right here, the coefficient in front of the x, and what you do is you take half of it. So the coefficient is minus 6, half is minus 3. Then what you do is you square that. So minus 3 squared is 9. So then what you do is you write the first two terms exactly the way they are, and then you add this guy right here, plus 9. Then immediately subtract it, and then complete it with what's remaining, which was the minus 2. Now the magic that happens is that part of the equation is now able to be factored. So in this case, it's x minus 3 all squared. And then this part of the equation just becomes negative 9 minus 2, which is minus 11. So this is what's known as completing the square. Now, that's pretty straightforward, but we've got to do it with this big guy here. And then somehow we have to figure out the rest of the question. It shouldn't be so bad. I'm just going to do it carefully, and hopefully it'll make sense. Now you might say, well, what's the point of completing the square? I don't understand. Like, okay, I saw how you did it, but what was the need to do that? Well, what it gives us is the maximum or minimum, and I'll explain with a graph here, a very basic graph. So this is the function, right? So if we had a little graph here, let's say, this function opens upwards like this. Now you say, well, how do you know that? Well, because the coefficient in front of x squared is positive. In this case, it's just a 1, right? And that's positive. So because it's positive, the graph will open upwards. If this was, say, a -1 or a -2 or whatever, some negative number, it would open downward. So I'm confident that it opens upward because it's positive. Now, what it looks like, I have no clue. But so I'm just going to draw it in like this, something like that, right? I don't know what it looks like. But what this tells me is that, let me draw it a little bit better. Yeah, like that. What it tells me is that when x is equal to 3, this part vanishes, right? It becomes 0. And that's when this function attains its minimum value. So if this is the x-axis and that's 3, and on the y-axis, which is right here, this isn't drawn to scale, obviously, but that would be 11. You see? Y being the equivalent to f at x. So that's the whole point of completing the square. You can get a minimum value or a maximum value if the parabola was opening like that, meaning it opens upside down as to what I drew over here. All right? Okay, so that's clear. All right, so here we go. Well, let's see if we can continue with this question without losing any of you. Okay, so first thing we have to do is we have to expand this guy out. And some of you are very comfortable with summation notation, some of you are not. Not a big deal. Try to do it in a way that is very easy to understand. So f at x equals this, right? So if I were to expand it, what would that mean? Well, when I is 1, this becomes x minus a1 all squared. And that's summation, so we have to add. When x is 2, when I is 2, I hope that's what I said the first time. When I is 2, this becomes x minus a2 all squared. Okay, when I is 3, this becomes x minus a to the power of 3. Not to the power, a3. You got to be careful here. And then dot, dot, dot. I hope you get the hang of it. Just keeps on going. And then the very final value for I is n. So that would be x minus a n all squared. So that's basically the expansion of that minimally scary looking function. Okay, great. How does this help us? Well, we have to continue expanding this and collect like terms. So I'll just do it for a few. We got x squared minus 2xa1 plus a1 squared plus x squared minus 2xa2 plus a2 squared plus x squared minus 2xa3 plus a3 all squared. And then dot, dot, dot to the very last one, which would be x squared minus 2xan plus an squared. Okay, now let's collect like terms. We have to collect all the x's, and there's how many x's? There's going to be n of them, right? So nx squared. And then you've got this minus 2x from everything, and then when you factor it out, you'll get a whole bunch of these a's, a1, a2, a3, dot, 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 all the way till an. And then you have a whole bunch of these ai squared plus a1 squared, a2 squared, a3 squared, dot, 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 all the way to the last one, which is an squared. Correct? Well, now, this is where you can add back your summation notation. This guy all in here is essentially just the sum from I equals 1 to n of ai. That's all that is. And then these guys all over here is basically just the sum from I goes to 1 to n, from 1 to n, of ai squared. Okay, so that's basically, we went from here to here to make it look a little bit pretty. Now, this is where we complete the square. This guy right here. This is where we complete the square. So let's keep it in the same, screen. And let's go ahead and complete the square on this guy right here. And remember, it's the same concept as before. Same as what I did down here. If you guys remember right here how I completed the square, it's going to be the same thing, but the notation is a little bit different, so it's obviously going to be a little bit more complicated. Okay, let's complete the square. So how do we do that? Well, remember, you take half of the coefficient, so it's nx squared minus 2, and then I'll put the summation first because I want that to be ahead of the x, ai, x, and then this guy is just the summation from I equals 1 to n of ai squared. Okay, all right, so let's do this now. Okay, so now that you got that there, let's try completing the square. Okay, so now we have to complete the square without making any mistakes on this guy right here, this whole thing. Now, in my earlier example where I completed the square, I gave you a very simple one, right? And this coefficient was 1. But in this case, it's obviously a little bit more complicated because of the summation notation. But in addition to that, it's not a coefficient of 1, it's a coefficient of n. But no problem, that can be easily handled by factoring out the n. So when you do, you just get x squared, and then you get minus 2 over n, and then the rest is pretty much the same. I equals 1 to n of ai x, and then that's it. You don't have to factor it from the last term, which is the sum of I equals 1 to n of ai squared. So just a little bit of a additional step, I guess. Okay, now the remaining of the question is the same. You have to complete the square. And if you remember, how do you complete the square? Take that coefficient, take half of it. So if you take half of it, it would be just 1 over n, and the sum from 1 to n of ai. And then you have to square it. So if you square that, it will be 1 over n squared, and the sum from I equals 1 to n of ai, all squared. Okay, so that is what we have to add and subtract. So here we go, x squared minus 2 over n, the sum of I equals 1 to n ai, and then we have to add and subtract this guy right here. So first let's add it, 1 over n squared, the sum from I equals 1 to n of ai, all squared, and then let's subtract it, 1 over n squared, the sum from I equals 1 to n ai, all squared. Close the bracket, and don't forget that last guy right there. We can just squeeze it in here. The sum from I equals 1 to n of ai squared. Okay, now remember the magical part, which is this part factors. And in this case, it looks like it will be x minus 1 over n times this guy, which is I equals 1 to n of ai. Right? Hopefully have not made any mistakes. And that's all squared. And then we remember that this part is still in the brackets. So if we're going to kick it out of the brackets, don't forget to multiply by that n. I think that's a big mistake that people make. And when you do, you get minus 1 over n. And then this just becomes the same, which is I to n, 1 to n of ai all squared. And then don't forget that guy, which is plus the sum of I equals 1 to n of ai squared. Okay, so now we have a similar situation. That if you recall right here, this tells us that this parabola, whatever it is, opens upwards, correct? And if you go back to the original equation, right, which is all the way, where is it? Here. These are all positive numbers. So that means that if you were to take x minus a positive number and then square it, that means anytime you square something, it's going to be positive. So that means f of x is always going to be positive. Now it could be 0 if x is equal to ai, if x was equal to all the ai's and so on. But we know for a fact that it's going to be positive or 0. So f of x is always going to be greater than or equal to 0 just from the nature of the fact that it's a square. So that means that f of x, if we were to draw this little graph, is always going to be positive. So if this is f of x and this is x, the graph is always going to be above the x-axis. And because this n is a positive, n just represents a number, a positive number of terms, it's going to be opening upwards. So it's going to be something like this. It's going to open like that. So that means that this has a minimum value. And the minimum value is right here, whatever. When x is something, the minimum value of f of x will be something. Now that means that we can look at this. When x is equal to this guy, 1 over n times the sum from I equals 1 to n of ai, this part of the equation vanishes, right? It becomes 0. And when it does, you obtain this, which would be the representation of its minimum value. So the minimum value will be this. And that minimum value is greater than 0, as we have illustrated in our graph. So that means that this minimum value, which is the, let's see here, minus 1 over n, the summation of I equals 1 to n of ai all squared, plus the sum of I equals 1 to n of ai squared, is greater than or equal to 0. It's positive, or it could be 0 in a very unique situation where all the x's are equal to all the ai's. We go back to the original equation to look at that. Given positive numbers, blah, blah, blah. If all the x's, if x was equal to all the ai's, then it would be 0. Otherwise, it will be a positive since it's a square. And when you square a number, it's always going to be positive regardless of what's inside the bracket. Okay, so we have proven this. So I guess at this point, we can just put it into a nicer format. I equals 1 to n, ai squared. Kick that negative over to the other side, make it look a little pretty. I equals 1 to n, ai all squared. And this is what they wanted us to prove, this guy right here. If you don't believe me, let's go back and look at the original question. There it is. Let's see if I can put it all on the same screen here. Yeah, they wanted us to prove this, and that's what I did. That the sum of I going from 1 to n of ai squared is greater than or equal to 1 over n times the sum of I going from 1 to n of ai all squared. So as you can see, just by completing the square and making sure you don't make any algebraic mistakes, we're able to figure all this out. Great. Let's move forward to the second part of the question. The sum of 16 positive numbers is 100. And the sum of their squares is 1000. Prove that none of the 16 numbers is greater than 25. Okay. So again, sometimes you think, well, how do I begin with this? Well, this is part B of the same question. And it's part B for a reason, because it's a continuum, meaning the first part of the question is going to help you with the second part of the question. And the first part of the question is right here. So that is what's going to help us solve part B. So first of all, let's just assign some letters here. 16 positive numbers, right? So A, B, C, all the way to P. So A plus B plus C plus D, dot, 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 all the way to P, I believe is the 16th letter of the alphabet. And they're saying that that is 100. And then when you square them, A squared plus B squared plus C squared plus D squared and so on, those dot, 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 all the way till P squared, they're saying that is 1,000. And then they're saying, prove that none of these 16 numbers is greater than 25. Okay, well, let's just implement this. Let's see what we get. In this case, we are told it's 16 numbers. So that means our n in this case is 16. So from that formula up there, that means the sum from I equals 1 to 16 of ai squared is greater than or equal to 1 over n, which in our case is 16. The sum from I equals 1 to 16 of ai, that whole thing squared. Okay, well the sum, this guy right here, of ai squared is right here. And that is 1,000 in our scenario. Is 1,000 greater than this? Well, this is 1 over 16. The sum of just the numbers from 1 to 16 of AI, A1, A2, A3, is 100. Okay, and then we got to square that. When you do this math, this side becomes 625. Is 1,000 greater than 625? Yes, it is. So that checks out. So that means our beautiful inequality, or whatever you want to call it, holds true. Okay, great. But I still haven't proven this part of the question. That's what I have to prove. Okay, I think I can do that. The way to prove that is to let P be the largest. This guy right here. We'll let it be the largest of all the numbers. And then we'll represent it as being equal to the others. So for example, from this equation, you get that P is equal to 100 minus A minus B minus C minus D minus dot, 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 all the way till O, right? That's the letter before P. And then from this equation, you get that P squared is equal to 1,000 minus A squared minus B squared minus C squared minus D squared, dot, 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 all the way till O squared. Correct? Okay, great. So now we use a little bit of our summation notation. This essentially is just 100 minus, let's put it in brackets here, the sum from I equals 1 to 15 this time, because remember, we took out P, so there's 15 left, of just AI. Correct? Because this is just, when you take out the negative, it just becomes a sum of A plus B plus C, and there's 15 of those. And then from this guy, if you put in summation notation, it's 1,000 minus the sum from I going from 1 to 15 of AI squared. Correct? Okay, great. Now what we have to do, I think this should be a negative, not an equal sign. Okay, great. Okay, so now we have to go back and use our wonderful equation and put these two guys in there. So let's do that, if I have any space. So this guy, the sum from I equals 110 of AI squared, if we were to first put this on one side, the sum from I equals 1 to 15 of AI squared is equal to 1,000 minus p squared, right? I just put it on the other side. And then from here, this guy, the sum from I equals 1 to 15 of just AI is 100 minus p. So these are the two guys I'm going to put into my equation up here. So the first part, which is on the left side, is just 1000 minus p squared. And that's greater than or equal to this part, which would be 1 over n. N in this case is 15, so be careful there. And then this part right here, this whole thing, would be right here, 100 minus p. And then remember, you have to square it. So this is what we're boiled down to, and that will help us prove this sentence that none of the 16 numbers is greater than 25. What I assume will happen is you're going to get a quadratic, and the quadratic parabola will be kind of like something like that, and then I'll be able to figure out these two roots and take it from there. Okay, I'll explain it, but that's what I'm thinking is going to happen. Okay, all right, so we're pretty much down to here. So here we go. I'm going to expand this out, put everything on one side, that kind of thing. So let's see here. Let's multiply through by 15, make our life easier here. 15,000 minus 15p squared greater than or equal to this guy, and then let's just expand it all out. It's going to be 10,000 minus 200p plus p squared. Put everything on one side. When I do, I get, let's see here, 16p squared minus 200p minus 5,000. And that's all less than or equal to 0. Okay, great. Off the top of my head, I don't know how to factor this, so I'm going to unfortunately have to use a quadratic to figure out what the roots are. So what was it? Minus b quadratic equation plus or minus the square root of b squared all over 4 minus 4 ac all over 2a. You guys remember that quadratic formula, right? So do the number crunching and you get 200 plus or minus, this turns out to be 600, and that's all over 32, and that gives me values of p equals 25 and negative 12.5. So that means that if this is a quadratic formula, which it obviously is, and you were to draw a sketch of the graph, the roots are 25 and minus 12.5, and the coefficient was 16, so that means it opens upwards. So like that. And this is very important. They're saying that they want the quadratic to be less than 0. So they want it to be in this range right here. Less than 0, meaning below the x-axis. And therefore, in that range, the largest value of x is 25, as you can see from the graph. So there we go. Largest value. Well, in our case, we're using the letter p. So I guess you can put p instead of an x. Largest value of p is 25. And since p was used to represent our largest integer, if I could find it, yeah, right here, right there, p was the largest, and I just said that the largest value of p is 25. We just proved that none of the 16 numbers is greater than 25, since the largest is 25. So there we go. It's a very good question. Number 3 really just involves completing the square and making sure you don't make any algebraic mistakes.